Today, we're doing something really exciting. We're bridging that massive gap between textbook theory and a functioning real-world utility-scale PV plant. Look, you've already made it through the fundamentals, right? You know the commercial metrics, you can calculate return on investment, and you've got yield estimates down. But now we're standing at the absolute threshold of heavy, uncompromising engineering. We're going to take everything we've meticulously studied in Chapter 4, all those detailed electrical components, the sizing methodologies, the design basis, and forge them into the exact tools you'll use to design massive solar installations. We are officially transitioning from learning concepts to preparing to move earth, lay copper, and safely channel millions of watts of raw power.
But before you even think about firing up your design software, you really need to internalize this core truth from your training manual. Design does not begin with a drawing. It begins with a deep, profound understanding. You have to know exactly how power is consumed, how the solar resource behaves on your specific site, and the unyielding physical realities of the grid you're connecting to. I mean, if you don't actually understand the soil resistivity of your site, your grounding calculations are pretty much useless. A complex AutoCAD drawing is just a pretty picture if it's going to fail in the field. We are engineering reality here, and reality doesn't forgive bad math.
So, here is our blueprint for today. We'll cover the Chapter 4 Master Summary, MV switchgear and transformers, cables, earthing, and SCADA, sizing methodologies and design basis, your Chapter 4 assignment, and finally, Chapter 5 final assessment.
Section 1, Chapter 4 Master Summary.
Let's do a quick recap of the individual components we've studied, because every piece of infrastructure is part of a deeply connected web. You've got your medium voltage switchgear, that's the beating heart of the facility. Then your transformer stations doing the heavy lifting of voltage conversion. The miles of AC and DC cables act as your arteries, while the earthing and lightning protection systems shield the entire asset from sudden disaster. And lastly, SCADA, which is your central nervous system. These absolutely do not exist in isolation. A flaw in the arteries triggers the nervous system, which then immediately shuts down the heart. You're engineering a living ecosystem that has to operate cohesively and safely for decades.
Section 2, MV switchgear and transformers.
When we talk about medium voltage switchgear, this is the sheer physical reality you're dealing with. It's a massive, robust lineup operating at up to 33 kilovolts. Every single one of these metal-clad cubicles houses live power circuits, intricate controls, and heavily calibrated protection mechanisms. Whether it's handling day-to-day full-load currents or containing massive short-circuit faults, this equipment has to be engineered flawlessly to isolate catastrophic issues in mere milliseconds.
And that's exactly why establishing your design basis is so critical. Take this 9 MVA step-down power transformer, for example. You aren't just guessing here. You're defining non-negotiable parameters, stepping down 33 kV to 0.8 kV, specifying a DIN 11 vector group, and locking in a 6% impedance voltage. And why does that exactness matter? Because being just 1 percentage point off on your impedance completely changes your short-circuit thermal calculations downstream. These numbers create a mathematical butterfly effect that dictates the safety of the entire facility.
Section 3, Cables, Earthing, and SCADA.
Connecting all this massive hardware means balancing physical capabilities against strict project economics. For cables, you're constantly weighing the lower upfront cost of aluminum for those long MV runs against copper's vastly superior conductivity and space-saving perks. Same goes for insulation. Is standard PVC enough, or do you need the 90-degree thermal limits of XLPE for heavy-duty applications? This isn't just an electrical choice. It's a massive financial one that sets your capital expenditure budget.
Which brings us to grounding. To ensure personnel safety during fault conditions, your earthing network has to strictly hit these targets. We're talking less than 5 ohms for MV equipment and less than 3 ohms on the DC side. More importantly, your step voltage cannot exceed 116 volts, and touch voltage has to stay under 73 volts. Hitting these targets, especially in arid desert soil, requires a meticulous grid of buried copper. It's quite literally the difference between life and death for technicians on site.
And all this physical infrastructure ultimately reports up to SCADA. As the plant's nervous system, it monitors critical energy meters, reads fault alerts from protection relays, and tracks real-time weather data. It takes hundreds of acres of high-voltage chaos and ties it into one readable, actionable digital interface. Without it, you're flying totally blind.
Section 4, Sizing Methodologies and Design Basis.
We've seen the hardware, but mathematics is what holds it all together. Every single cable and circuit breaker selection requires executing these 3 sequential steps. First, calculate the full load current.
Second, size your circuit breaker with a 1.25 safety multiplier. Third, execute a short-circuit thermal check to make sure your conductor won't literally melt into slag during a dead short fault. And if it fails step 3, you can't ignore it. You have to iterate. Go back to step 1 and upsize your cable until the math works perfectly.
Oh, and don't forget your cable sizes are also restricted by strict voltage drop limits. Look at how exceptionally tight that medium voltage tolerance is, just 1.5%. When you're running cables for kilometers across a sprawling solar field, staying under 1.5% requires incredibly precise sizing. If you miss this, you're just losing megawatt hours to pure heat dissipation in the dirt, draining project revenue every single day.
Section 5. Your Chapter 4 assignments. Okay, here's your task list for Chapter 4. First, you need to scratch out the very first block drawing for the MV infrastructure. But you're not stopping there. You have to draft a complete, professional report showing the design basis and exact sizing calculations for every single component of the network. I mean everything. The MV switchgear, transformer stations, cables, earthing and LPS, SCADA, literally every detail we've had in training. You even need to include the inverters and the module table mounting structures. This is a crucial rite of passage to prove your network components are correctly sized. Section 6, Chapter 5, Final Assessment.
So, why are we pushing you so rigorously on all these sizing methodologies and this massive design basis report right now? Because Chapter 5 is your final assessment, and it features a practical design workflow for a massive 60 megawatt peak PV plant, fully integrated with a 20 megawatt-hour battery energy storage system, and it's all happening at the 33 kilovolt level. Integrating vast solar generation with chemical energy storage at high voltages leaves absolutely zero tolerance for sizing errors. The foundations you lock in right now are what will keep that 60 megawatt beast stable. The tools are in your hands. You know the hardware, you know the underlying methodologies, and you understand the immense reality of high-voltage engineering. So dive into this assignment and trust your calculations. Because when we get to Chapter 5, that plant isn't going to design itself. The only question left is, are you truly ready to harness that kind of power? Good luck, and I'll see you in Chapter 5.